Okay, got the recording turned on. We are going to change gears fairly dramatically from how classes run since day one to now, and then how we're going to run for the rest of the semester. So we have spent 11 chapters talking about the basics of organic chemistry. Who's got electrons? Why are they there? How are they going to share them? What are the trappings of electrons moving between species? All that sort of stuff. A question that you may have had this entire time is, how do we know that any of this stuff actually works? When we say that like A plus B forms C, how do you know, right? If I just pick up like a thing of coffee and go, oh yeah, there's definitely like theobromine in here. Is there? Maybe, I don't know, I can't really smell it. How do we determine if we have the molecules that we think that we have? So what we're going to be spending some time for the next couple of weeks talking about is spectroscopic measurements, using instruments to determine chemical structure. There are lots and lots of these. For an organic chemist, the three primary ones we're going to use are mass spectrometry, called MS, infrared spectroscopy, called IR, and then the most important one is called nuclear magnetic resonance, NMR. I'm going to talk about mass spec and IR together. I might get through all of this today. We're going to go through it pretty quick. They're not that hard. It's going to sound a little more technical. It's a little more boring because I have to do this from PowerPoint, but don't worry, I can still write on my PowerPoints, right? So there'll be some writing here. But then we're going to spend the vast majority of our time talking about NMR because it is more important and I think they're harder. So let's go through first mass spec and infrared spectroscopy today, maybe into next week, since we are not going to have class on Friday. Right? So no recorded lecture, none of that. You just get a day off. Happy early Thanksgiving. The two techniques, like I said, we're going to be talking about here are mass spectrometry and infrared spectroscopy. Let's talk about mass spec first. Mass spec determines the molecular weight by measuring the mass of a molecule. There has been a huge, and sorry, I'm going to be going off camera here because I can't sit behind a podium for too long of these things. There has been a huge amount of progress made with mass spectrometers in my lifetime. The mass spec that I learned on was the size of like this tea bowl and cost like $1 million at the University of Oklahoma. They now have suitcase mass specs. So I like to think of this kind of like Iron Man, right? So if you've seen the first Iron Man movie, he made the suit and it was like big and clunky. And then by like Iron Man 11 or whatever we're at now, it was a suitcase that he had. Same thing, but it's been getting smaller and more efficient the entire time. Mass spec is doing that. And the reason that's so exciting is we can now use mass spec to go into a field and measure directly at that source. This is hugely important because if you can measure accurately the molecular weight, you can take a pretty good guess as to what the molecule is. Because when I say accurately, I mean like 4 decimal places accurately. So for instance, a place that a mass spec has really come in handy recently, for a sad reason, but a geopolitically important reason, is several years ago, Bashar al-Assad, the current president / dictator of Syria, used chemical weapons on his own people. And the UN put a bright line saying, you cannot do that. If you use chemical weapons on your people, or on anybody, that is a war crime. And so making that accusation is a huge deal, right? That's an act of war to be able to say, this is a war crime, we're going to respond to it in kind. So you need to be able to get that answer right, to be able to say if this happened or not. So there were some UN scientists that went into Syria and took samples of dirt, put it into a mass spec in the field in real time, and were able to measure some nerve agents that we used. Now, the international community, in my regard, failed at that point because we didn't do anything about it. But that wasn't previously possible. Because if I was going to go into Syria and take a scoop of dirt and then ship it back to a lab, even in Europe, the sample's going to degrade before I get it there. So the miniaturization of mass spec has had a huge implication in being able to do measurements in real time for sensitive samples, both illicit and legitimate. Every mass spec has really 3 components to it. One of the things we need to do is get the sample into the instrument, and we do that by ionizing the sample. We need to be able to separate out if you have a mixture of things. So imagine if I take a scoop of dirt, there's like a lot of stuff in a scoop of dirt. So I need to be able to separate all the molecules away from each other, and then I need to be able to detect them. So a mass spec makes the sample readable, separates out complex mixtures, and then detects them once they're separated out. I'm going to show you a couple different versions of this, but they all behave kind of the same way. The way that a mass spec is going to work is you're going to take an organic molecule. So this is our favorite thing, R, right? The generic organic molecule, and we're going to hit it with a beam of electron density. So it's actually not always an electron beam, but it can be different things where you're going to wallop a molecule and knock an electron out of it. So this is going to make a radical cation. So we know a single electron is a radical. It now has a positive charge, so that's a cation. That's important because most mass specs can be the detector is just a wire. So if you envision, I've got a wire between my two hands here, it's got a charge running across it. If a charge hits that wire, my current will change in the wire. But if a neutral species hits this wire, I won't be able to see it at all. So mass specs can only see things that have a charge. And that's why we want to break these down into things that have cations in them so that we can register them with our wires that we're using. The real trick here is how much energy do I put into the molecule to be able to turn it into something that has a positive charge without obliterating it? Because what we're really talking about here is kind of like a James Bond villain sort of laser, right? If you hit a molecule with enough energy to knock an electron out of it, you hit a molecule with enough energy to blow it into pieces. And so that's a consequence of mass spec as well. Sometimes you're going to take a molecule, often people take a molecule, hit it with so much energy that it breaks into multiple pieces. And so what you see in the mass spec is not the whole molecule, but pieces of the molecule. So then you have to come back through and say, well, my original molecule had a green mark. My original molecule had a red pen, a green pen, a red cap, and a green cap. I hit it with electron density, and now my mass spec tells me I have these 4 parts, right? So now I, as a scientist, have to go back through and say, how am I going to put these parts back together that make sense? Well, I know some stuff about this, so maybe the green cap goes in the green pen, so that was one piece of the molecule, and the red cap goes in the red pen, that was one piece of the molecule, and then maybe they connect together. So I'm looking at the debris of what came off and reassembling it to say, oh, this is probably the starting material that I began with. As we do this, so whenever you hit the molecule and it breaks up into pieces, that's going to fly through the machine, and we're going to separate those pieces out. Most of the time, they are based on their weight. If I were to throw a baseball across the room, it would be hilariously slow because I have a terrible arm. But it would be a lot faster than if I tried to throw a bowling ball across the room. So I can launch a baseball pretty quick. A bowling ball is going to basically just roll away from me. Same thing is true with molecules. Light pieces of molecules travel through the instrument very quickly. Heavy pieces of the molecule travel through very slowly. Our mass spec is going to show how those pieces come together in what's called the mass to charge ratio. So this is important. The mass is going to tell us how much the fragment weighs. The charge is really the most important piece of this, because if you don't have a charge, the molecule does not show up on a mass spec. If you have a +2 charge, the molecule will look like it weighs half as much. So let's use me as an example. You hit me with an electron beam, I'm like, hurts, lose an electron. I basically weigh the same amount that I do now. People are always surprised to hear this, but I weigh 200 pounds. I know I look like I weigh like 80 pounds, but 200 pounds, right? So if you knock out an electron from me, I still weigh 200 pounds because an electron weighs basically nothing. But if I get hit with a beam and I now have a +2 charge, the mass spec is going to say, oh, Nathan weighs 100 pounds because my mass is being divided by a +2 charge instead of a +1 charge. So it's one of the things you have to watch out for with a mass spec is the charge must be present and it matters. If you have a +1 charge, the mass is what the mass is. If you have a +2 charge, it will look half as heavy. That's not very common, but something to be aware of when you guys go get your big fancy jobs running mass specs. Okay, here is an instrument. So the way this is going to work is you have, I guess I better sit back here so I can direct with this. You have a place where the molecule is introduced and ionized. So you'll typically put it in some organic solvent and you'll heat it up so it turns into a gas. And then this is our James Bond villain beam. So when the molecules come up and hit this beam, they go, and they get excited, electrons get knocked out of them, and they break into pieces. A little window opens up over here, and the molecules feed into this tube, which is in a vacuum. Inside this tube, which makes a right-hand turn, there's a magnet on top and on bottom. These are permanent magnets. What do you guys know about charges that move? Anybody know about the right-hand rule? Who's taken physics? Let's start with this. A couple of us, raise your right hand if you've taken physics. There's this thing in physics called the right-hand rule where you can, and you get the coordinates. You guys know what's up for some of you. If you've not done this yet, this is the universal symbol for I hate physics. The right-hand rule tells you about if you have a charge that's traveling, so in this case, in the direction of my thumb, you can measure the magnetic field that it's producing because charged particles that are moving create a magnetic field for reasons that I don't understand that are spooky to me. That's just a physics thing that happen. So if a charge is traveling this way, the magnetic field goes like this. Right-hand rule. It'd be fun. The left-hand rule doesn't exist because people hate left-handed people. I'm deeply offended by the physics right-hand rule. What I'm trying to say here is as our particles travel through here, they're charged, they're moving, they are little magnets. So they're going to respond to a magnetic field that's induced on them. And the idea is that I can tune, so if this is, here's my hand. I'm going to try and make this as entertaining as possible. I know it's stupid. Okay, I'm over here. I get hit with an electron beam, turned into ions. I go into the slit, I'm traveling down this, and now I am going to run head into this side of the turn. If there's no magnetic field, I'm going to just travel in a straight line and go, and I'm out. I don't make it to the detector, which is over there. Now, if I turn this magnetic field on and I tune it just right, I will be charged, traveling along, creating my own little right-hand rule magnetic field. I hit my magnetic field here and I go, oh, I'm going to turn this way. Then I hit the detector. So by changing up the strength of the magnet, I can change up what size particles make the turn. And that is what we call a magnetic sector or magnetic analyzer to be able to pick through the different particles that are going to make it. Low magnetic strength means only light particles are going to make it through. The heavy ones just barrel on through and hit the wall. High magnetic strength, the heavy particles are going to make the turn. The light particles are going to turn too much and crash out on the wall as well. So by changing up the nature of this magnet, that's how we're going to select for the particles that make it to our detector. Again, our detector, you can think of it just as a charged wire. So it doesn't know what's hitting it. It just says, I have current, wait, something hit me, mark it. I have current, wait, something hit me, mark it. So if we know when things are hitting the detector, and we know how strong the magnet is, we can infer what the mass is of the particles hitting that detector. And we're going to put those two things together to be able to show a mass spec that I'm going to show you in a second, because this is the one that I learned on. And it literally, it's not inaccurate to show it. I'm going to make another Iron Man reference. Sorry, so many Iron Man references today. You guys seen Iron Man, is it 2, where he's got the big cyclotron in his basement? Here's like the big steel tube. You guys know what I'm talking about? It's one of the Iron Mans, right? He like makes a new element for his little chest. Is it 2? All right, cool. That thing that he built in his basement, the big round tube, which 3 of us know what I'm talking about. So this is a great metaphor. Looks a lot like the mass spec that I learned on. There's this huge steel tube. It's like this massive thing. It's not practical. You wouldn't take it anywhere. You would bring the samples to the lab and run it there. This thing would weigh, tons and tons. And literally you could, like the path I just walked would be the actual instrument. We've been able to miniaturize it by using a very similar idea, but called a quadrupole. It's called a quadrupole because it has 4 poles. So quad pole. What we do here is we put charges on the poles. So pluses on one side, minuses on the other side. And you can change the amount of positive and negative potential in these rods so that as your sample moves down through here, it'll get pulled one way or the other. And depending on how the rods are tuned, only certain size particles will make it all the way through. So this is handy because you don't have to have this big wide turn. You don't have to have it in a perfect vacuum. You need a vacuum, but you can miniaturize this a lot more because you're just using charged wires as your path. So this is how we turned these mass specs into like a suitcase that you can take out into the field, because a quadrupole MS is just as accurate, but it's much, much smaller and much more affordable. I'm moving kind of quick here. 1, because I'm going to lose you guys real fast. And 2, because it's not that important. Are you with me so far-ish? 2 Iron Man references. He also did the thing where he walked around. He's trying. He's putting in the work over here. Okay. The part we really need to know how to do is how to read a mass spec. Unfragmented is absolutely a word, PowerPoint. Get off my case. When you plot a mass spec, this is what it's going to look like. So on the y-axis, you have relative abundance. that goes from 0% to 100%. Every mass spec will always have 100% signal. Because what it's doing is it's just counting, it's what we call binning things that are hitting it. So if I have one red pin hit my detector and two green pins hit my detector, which is my head apparently, I will say, ooh, I had more green pins than red pins. The green pin is 100% my signal. So the red pin is 50% of what I saw of this. You're always going to have some base peak that is registered as this is 100% and everything is going to be measured against that peak. You also will have, so this is the base peak. You will also have a parent peak. The parent peak is the heaviest peak in the spectrum. So down here on the x-axis, we have the the mass to charge ratio. So on this side, we have very light fragments. On this side, we have heavy fragments. And as we go from left to right, they get heavier. So the peak furthest to the right is the heaviest peak that we call the parent peak. All the other peaks that show up in here are the parent peak that's been broken into pieces. Now, the parent peak sometimes will also represent the molecular ion. That is, bless you, did Dr. Green get hit with an electron beam and he stayed together and went through? I would be the molecular ion. If I got hit with the well, I'm not going to make it me because it's scripts. If it was a Lego version of me and it got hit with an electron beam and it blew up into pieces, that would not be the molecular ion. There would be just a chunk that went through. That's why I made it Legos, because otherwise I'm getting very violent towards myself. So the molecular ion is not always going to survive. Sometimes a molecule is going to hit that beam and blow up into pieces, but there will always be a base peak and a parent peak. And I guess sometimes the parent peak can be the base peak, but there'll always be something that's the highest, 100% base, and heaviest parent. Let me come back to that in a second. Those two things are super important. Like if your organic chemistry professor was going to test you about mass spec, some basic information they would want from you, not this class, but a class, would be like they would give you a mass spectrum like this one, and they would say, hey, y'all, you should label the base peak and the parent peak. And you would do exactly what they just did here, and then you'd get full credit for that problem. Right? Cool. Here's a way that you can use a mass spec to be able to identify a sample. So a way of doing this is to run what's called a tandem mass spec, or MSMS. So what that means is you run the mass spec, you run a sample through a mass spec, but instead of a detector on this side, it's another mass spec. And the reason you'd want to do that is the first mass spec is kind of your coarse separation. The second mass spec is your fine separation. And that's handy because let's say that I go out into Damascus and I take a scoop of dirt and I see that there is a molecule in there that has a molecular weight of 72. Well, that's not super helpful because 72 can be multiple different things. C5H12 and C4H8O both have a molecular weight of 72. Well, those are clearly different molecules. One has oxygen, one has 12 hydrogens. They're different. Right? But I can use the exact mass, this AMU stands for atomic mass units, and know that C5H12, if I average out all the isotopes in there, has a molecular weight of 72.0939, 4 decimal places. The formula C4H8O has an exact mass of 75.0575. Those numbers, by the way, are coming just from the periodic table of taking the average masses of those atoms, adding them together, but just really getting into the decimal places. These numbers are different, really far out into the decimals. So if I did a double focusing mass spec or a tandem mass spec on my sample, and I saw that it was 72.0939, I could say, ooh, it's this one. I can eliminate C4H8 because my exact mass didn't match. That's why you see tandem mass spectrometry used a lot more frequently these days because it's so much more sensitive. And again, some molecules, especially warfare agents, are reactive. That's the reason they're so bad for us, is they get into your body and they cause havoc, but that also means they degrade very quickly. So if you want to be able to tell that some molecules are there, you have to read them in real time or they'll fall apart before you ever get them back to a lab. This just wasn't possible like even 10 years ago. But it is now. Okay. You guys with me so far? Ish. Okay. Hopefully the Syria thing is not too controversial. There's other examples of this, but I think like generally speaking, like don't use not even just Assad. People, human beings, should not use chemical weapons against other human beings. Chemistry is a way that you can help to, one, create weapons, but also detect and prevent them. And so I think that's why it's an important piece of this lecture. Here's a way of trying to interpret a mass spec. So if I took a mass spec of 2,2-dimethylpropane, let's draw that out. Dimethylpropane, that's CH3, CH2, CH3, that's propane. 2,2-dimethylpropane would be a methyl group here and a methyl group here. And so there's 5 total carbons in that molecule, right? CH3, C, CH3, CH3, CH3. If I put that molecule into a mass spec and I hit it with an electron beam, this is what I get. So students, who I'm definitely going to ask this question about on the next quiz, whenever that happens to be, where is the base peak in this spectrum? What is the number of the base peak? 57. Bless you. What is the parent peak? Also 57. This is furthest to the right, and it's the tallest. This is both the base and the parent peak. You just got some points. Great job. Yeah, so, okay, so it's the parent peak because it's the heaviest. So it's there are no peaks. These little peaks down here are isotope peaks. We'll cover those in just, actually, I'll tell you about them right now. Most of carbon in the universe is carbon-12, right? 99% of carbon in the universe is carbon-12. 1% of carbon in the universe is carbon-13, well, a little less than 1%, is carbon-13. That's what these are about. It is highly unlikely that you'd have a molecule that would have all carbon-13s, but it's probable that out of the trillions of these that are in your sample, one of these carbons would be carbon-13. Mass spec can read a carbon-12 versus a carbon-13 because it's very sensitive. So you'll see little peaks in here. This peak is the base peak because it goes all the way up to 100%. It's the parent peak because there's no other peaks out here. See that? It's so good. This is normally around the time. Actually, I'll just go ahead and bring this up because I think it's always funny in this class. Right before these lectures, everyone's like, I am so stressed. I hate this class. I can't take any more of it. And then I start doing lectures from PowerPoints, and every time, maybe not right now, but by next week, students will be like, can we go back to the thing that I was super stressed about? Because I like that a lot more. We'll do a lot more interaction here. I know this is not my finest hour. Base and parent peak is right here. Here's the weird thing. The base and parent peak, and really the parent peak, is 57. If you add up all the atoms, C5H12, and then you do all the periodic table math there, carbon's worth 12, hydrogen's worth 1. So 5 times 12 plus 12 is 72. Well, 72 would be like over here, right? There's no peak over there. So what does that mean about our 2,2-dimethylpropane? Everything blew up, right? I put 2,2-dimethylpropane into my machine. I hit it with an electron beam, and the poor dear did not survive. Only pieces of it came off. So we don't see the molecular ion peak. There is no molecular ion peak because it would show up around here. So what do we think a parent peak of 57 represents? Let's do a little bit of math here. And this can be annoying, but I'll do it long form. I don't see 72, but I do see 57. What is the difference between 52 and 70, or 72 and 57? 15. I am missing 15 grams per mole from where I should have a peak to where I have a peak. How can you get to 15 grams per mole? Fantastic. A carbon, which weighs 12, and 3 hydrogens, which weigh 1 apiece. That represents 15 atomic mass units or grams per mole. They are equivalent. So what is this peak? It is my 2,2-dimethylpropane that lost a methyl group. I took 2,2-dimethylpropane, I hit it with energy, and I blew off a methyl group. Well, if I did that, I better see 15 somewhere in here. Well, it's kind of small over there, but there's methyl groups that are in here as well. So what we're seeing is this molecule, having blown off a CH3, has now only, so it had 5 carbons, now it's got only 4 carbons. It lost a carbon and 3 hydrogens when it got hit by my beam. We're seeing the fragments, not the full molecule. Does that make sense? Ish. You can do this for all the peaks in here, but I think, you know, identifying a couple is not a bad idea. That's what I just showed you on there, right? So we took our full molecule. If we had a molecular ion, it would weigh 72. We lost a methyl group, so when that got blown off of it, it made this, and so now our radical cation weighs only 57. Here's a much more likely example that you'll see. So hexane. It has 6 carbons, bunch of hydrogens in there. The molecular ion for hexane is 86. You can add this up by taking 12 times 6 plus 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 12 times 6 plus 14 will be 86, I promise. Adding up the molecular weights, the atomic weights of all those atoms. So if I look at a mass spec of hexane, what are the chances I'm going to only see a peak at 86? Pretty low, because I've got this big long chain, right? And I'm hitting all parts of the chain with my electron beam. So it's going to break apart into pieces. What are some likely pieces that we're going to lose? Well, just take your hexane and start chipping away at it one at a time, 1 carbon at a time. If we have hexane, it's 86. If I lose 1 carbon off of it, it would be 5 carbons and weigh 71. If I lost another carbon, it would be 4 1, 2, 3, 4, 5. 1, 2, 3, 4. If I lost another carbon, it would be a 4 carbon chain and weigh 57. If I lost another carbon, 3, another carbon, 2. I'm just breaking a methyl or a carbon off at a time and making the chain progressively shorter. Now, not all those peaks are going to be represented the same, because remember, my machine is separating them based on weight. And so some peaks are going to fly through my machine very well, and some peaks are not going to fly through my machine very well. So notice I've got a lot of this one, not very much of that. Oh, sorry, wait, I've got not very much of this peak, relative abundance of 10, a lot of this peak, a lot of this peak, and not very much of that. They're not going to be all represented the same, but they are going to show up. So a mass spec of hexane looks like this. You would see, in this case, the molecular ion peak, because it is at 86, and we know that hexane weighs 86, so that's good. The vast majority of it, though, is after it's lost a methyl group, it has turned into after it's lost an ethyl group, a CH3 and a CH2, has turned into our base peak over here. So where is the parent peak in this spectrum? 86. The parent peak happens to be the molecular ion peak as well. Where is the base peak in the spectrum? 57. What's this? It's the number 43. What does it represent? Yeah, so you could be doing the math in your head, but I gave you a cheat sheet up here. A 3-carbon unit with CH3, CH2, CH2 weighs 43. So that fragment is here. We're seeing the pieces of this. I think the Lego example is like a good one. Right? Have you guys seen like the Death Star Lego? I think Legos are getting out of hand. Back in my day, they were like little cute things. Now it's like you build like whole cities. There's an actual Death Star. It's like $3,000. If I had the Death Star up here, you guys would go, ooh, Death Star, really cool. If I dropped it, I'd be devastated and would break into pieces. But you could come up here and be like, oh, here's a big chunk with that like hollowed out part. And here's another big chunk. And oh, it's the Death Star, right? You're not looking at the whole piece of it. You're looking at the Lego fragments that are broken into pieces. And then you're mentally putting back together to say, oh, this is the Lego I started with. Okay. I have the most ridiculous acronym for you of all time. Some of you want to be medical researchers. Unclear why. Chemistry is way better. I'm just kidding. We need medical researchers. Chemistry is way better. The field of medical and biological mass spec has grown exponentially as mass spec has gotten better. But one of the things that has made this really hard is if you wanted to take a mass spec of, say, like a protein, you don't want to do it on an atom by atom basis because proteins have lots of atoms, right? We talk about proteins in terms of amino acids, which themselves have lots of atoms. A protein can be thousands of amino acids long. And so if you take a protein and you hit it with an electron beam, it's going to break apart. So instead of me having like the Death Star, which is, as I think my $3,000 model's like this big, imagine I had a dump truck full of Legos and I poured it out into the quad out there and I said, hey, what did we build with that? You'd go, I don't know, that's like the most Legos I've ever seen in my life. How could I possibly reconstruct that? So there's a technique we can use when we have really big, complicated samples, which is to put them into a protective sheath, hit that, and then break them into pieces that are more manageable. And so this is the two techniques that we use are called electrospray ionization, ESI, in which case what you do is you put your molecule into a droplet, you heat it up like water, you heat it up and put some charge into the room, and as the water droplet heats up, it gets smaller and smaller and smaller, but there's an electrostatic charge in there, so we're making those charges get closer and closer and closer together, and at some point your sample goes, and then it breaks apart. So we're not directly hitting it with a beam, we're just using the droplet getting smaller to kind of force them to move out. The other one that's probably more commonly used, or was more commonly used, is the really long name. Matrix-assisted laser desorption ionization, MALDI. What MALDI is you take a molecule, you put it into Jello, that's the matrix, and then you hit the Jello with a laser to blow up the Jello and your molecule to send it into the machine. So this is an example of that. You would have, let's say your molecule of interest is your molecules of interest are the little squares that are green and red. You put it into a matrix, which are the big blue squares. So I take my protein, put it into a Jello, let it sit there for a little while and harden up. I hit the Jello with a laser beam. It breaks apart both the Jello and the pieces of the molecule and the molecule that's in there. But the Jello takes most of the brunt of that laser. So when it blows up, the molecules that are in there basically stay together. All of that goes into my instrument. And then for these, we typically use something called a TOF, time of flight. That's the example of like, if I threw a baseball across the room, it's going to get across the room a lot faster than if I threw a bowling ball because it's so much heavier. So you can put these techniques together, a matrix-assisted laser desorption ionization, time of flight, MALDI-TOF instrument, to measure a particle that's in a matrix, have it travel through the machine, and then separate this out and saying, I know how much my matrix weighs because I made the Jello. So I'm going to just tell my machine to cancel out the Jello signal and measure only the particles that are in there. Has anybody done any biological research? Probably not at this stage, OChem 1 students, but you might do some work later on where you do protein characterization. And so there's millions of different proteins in our bodies. If you take a whole cell and you break it apart and you want to see all the proteins that are in there, mass spec is a way that you can determine what proteins are present. There's other things like SDS-PAGE and other techniques, but mass spec is one that's super important for it. Okay. Fortunately, I get to shut up for a second so we can practice these stupid things. These aren't stupid, they're important, but I don't like teaching from PowerPoint. Can you tell? Kane is actually about to fall asleep while making eye contact with me. Okay, I have 2 unlabeled samples. This is super embarrassing. I just poured some stuff into some beakers like I do, and I just set them out in the lab and I was like, uh-oh, which one's which? So I go and take a sample from beaker A, I put it in my mass spec, I get this reading. I go to sample B, I put my sample in there, I get this reading. I know that I had methyl cyclohexane in one of those, and I know that I had ethyl cyclopentane in the other. But here's the part that sucks, right? let's draw these out. Methyl cyclohexane. Cyclohexane looks like this. A methyl group would be attached to the top of it. There are 7 carbons, 14 hydrogens in that. Ethyl cyclopentane has 5, 6, 7 carbons, 14 hydrogens. They have the exact same molecular weights. That's not helpful. So I can't even do my double focusing mass spec. But I can use these two to figure out which one's which. How? Yeah. Start thinking about, like, if I was going to clip pieces off of these molecules, what are some likely pieces that I could pull off? Yeah, I love it. So over here in ethyl group, if we got rid of that, how much would this piece weigh? Or if we got rid of the methyl group, how much would this piece weigh? This one would weigh more, yeah? Yep. So I don't often ask you to do this, but get your calculators, which is our phones, of course, right? If I lose a methyl group from this, then I'm going to have 1, 2, 3, 4, 5, 6 carbons. So that's 6 times 12 is what? Okay. And then I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 hydrogens. So 72 plus 11, 83. This fragment weighs 83 atomic mass units. Do we think that this molecule came from sample A or sample B? Sample B, because look at that. There's a giant peak at 83. Well, gee whiz, where could that possibly come from? You could do the same thing over, sorry, before I move on, does that make sense? I took a methyl group off of this. I said, here's a piece. It's there. By the way, so that's a fragment that I just identified. What else is in the circle? The base peak. Where's the parent peak? There. Is there a molecular ion peak in here? So 83, that's 15. So 83 plus 15 should be 98. That's 98. This is the parent and the molecular ion. So my molecule did survive the mass spec here. Doesn't always, but this one did. How did I know it weighed 98? Because I calculated, so I did all the math for this one, right? To get to 83. If I add 15, because this is a carbon and 3 hydrogens, that equals 15 atomic mass units. I'm just adding 83 plus 15 equals 98. That would be my molecular ion. You see that? So this full molecule weighs 98 as well. There is a peak over here for 98. It's a little bit smaller. But notice that I don't really have much of anything here at 83. My big peak is down here closer to 70. So if I lose this ethyl group, I would have 5 carbons. What's 5 times 12? Plus 1, 2, 3, 4, 5, 6, 7, 8, 9. That peak would weigh 69. That's there. If I lose an ethyl group from this molecule, I end up with a peak at 69. That's pretty substantial. So I'm looking at the pieces of this molecule that blew apart and making a determination about what was there originally. So ethyl cyclopentane is here. Methyl cyclohexane is there. I probably wouldn't even go this granular. I am 100% going to ask you to label a base peak and a parent peak. I'll probably ask you to identify at least one fragment. And so if I have you do that, it's either going to be very simple math, or I will let you use a calculator if you have a hard time. I have a hard time making sure that my math is right as well, right? So you're going to see me work out the math on paper here because I just don't have good skills for even basic multiplication. That's just where I'm at. Questions about mass spec? No one is actively asleep. Mission accomplished. Let me tell you about, I'll just introduce infrared spectroscopy here. It does a little bit, it measures a different thing. So mass spec, what we're measuring is the atomic weight. And so really what you can get from mass spec is the molecular formula, right? At the end of the day, mass spec, molecular formula. Infrared spectroscopy uses infrared light to measure what functional groups are present. So let's talk about infrared light here a little bit. You might be aware of this, but the light we can see, visible light, represents a really shockingly small amount of electromagnetic radiation in the universe. It is a good thing that we can only see so much. If we could see radio waves and microwaves, you would freak out because there are radio waves coming to and from my phone right now. If I could see them and yours, I'd be blind because there would just be stuff coming out all over the place. So it's good that I can only see from like 300 nanometers to 800 nanometers. That's what we want. But just be aware that the light hitting your eyes is also, you also have ultraviolet light hitting your eyes and infrared light hitting your eyes. Infrared light is heat. If you have been to a restaurant where they are not so interested in your food coming out fresh once it's cooked, they will put the plate of food onto a stainless steel table and they will put a light on top of it. What color is that light? Red. They are not trying to make your food look evil. What that light is actually doing is transmitting infrared light onto your food, and it happens to also give off some red light as well. So you see the red light, what you don't see is the heat. But if you've ever stuck your hand underneath one of those heat lamps, you feel it, right? So right now, I don't feel any heat from these lights. But if I put my hand underneath a red light, infrared light, my hand would start to feel warm because there's infrared light hitting it. Molecules absorb infrared light. And when they do, it causes them to stretch and vibrate in such a way that we can determine, oh, this type of bond absorbed this much infrared light versus this type of bond absorbed a different amount of infrared light. And we can use it to determine the type of functional groups that are present. So mass spec tells us about molecular formula. IR is going to tell us about functional groups. We're going to use a really weird thing called wave number. So lambda, you may be familiar with, is the wavelength. So if we talk about the wavelength of something, that's like if I could see light in front of me, it's actually doing this. Waves are pretty crazy. Most infrared light is on the centimeter scale, so that's why you're seeing it here. The wave number that we're going to use is represented by a V. It's actually 1 over the wavelength. So larger wavelength is smaller wave number. It's kind of strange how we do that. So the deal is when we absorb heat, what's really happening is the molecules in our bodies start to move around. And in particular, the bonds start to move around. There's lots of different types of interactions that these can have. Oh, wait, hold on. This is one I actually need to show you. I put a lot of effort into this. That's my one fun slide. The rest are all serious and boring. Okay, so there's a lot of types of interactions where if I am, say, water, right? My chest is oxygen, there's a hydrogen, there's a hydrogen. When I absorb infrared light, my oxygens will start to move around, they'll start to stretch. You can have asymmetric stretching, you can have wagging, you can have scissoring, there's all sorts of motions they can have. And I think it's hilarious because when I think of IR, I think of molecules dancing. So this is a GIF of in-plane rocking, in-plane scissoring, out of plane, that's like this sort of motion. But really what we're talking about here is the molecules getting super jazzed about the infrared light hitting them. The Carlton is one dance that I think we can all recognize, even if you haven't seen The Fresh Prince of Bel-Air, but it is unique to him. Do not try and do this dance, it's his. It will forever be his. When you see the Carlton, you go, I know exactly who that is. When we shine IR light on a molecule, we know exactly what kind of functional group is there because of the dance that it's doing. So not every molecule, not every bond is going to do the same dance. The unique dances that we're going to see will tell us what's present. And one fun slide. So these come in lots of tables. I don't need you to memorize the whole table. I'm going to give you like 5 peaks, 5 regions that I want you to be familiar with. But what you can see here is like a CH bond. Nope, come back. A CH bond shows up in very different. Is that a laser pointer? Okay, it's back. This is why I don't do things in presentation mode. Okay, so a CH bond comes in a couple different flavors. You can have an sp3 hybridized carbon with a hydrogen, an sp2 hybridized carbon, so an alkene with a hydrogen, or an sp hybridized carbon with a hydrogen. And they show up at characteristic spaces, right? So just south of 3000 for an alkane, just north of 3000 for an alkene, and pretty far north of 3000 for an alkyne. So if I took an IR of an alkane, and an alkyne, I could tell them apart from each other based on where those stretches, where those particular dance moves show up. Here's an example of that. So this is hexane, this is hexene, this is hexyne. Now, what I want you to do is focus just here at 3000, because this line at 3000 is super important. Just at 3000, what's there? Some peaks to the right. So they're a little bit below. Those are CH bonds that are sp3 hybridized. Here's that same line at 3000. Well, now I have peaks that are both sp3 hybridized and sp2 hybridized. So what we're looking at is 1, 2, 3, 4, 5, 6. These carbon hydrogen bonds show up there. The other carbon hydrogen bonds in the molecule show up there. We can use this, and then same thing over here. My sp carbon hydrogen bond shows up really far away from that line at 3000. So we're just looking at where these peaks show up around 3000 to show us what kind of CH bond is present. In this case, I can tell an alkane from an alkene from an alkyne by using IR. I'll come back to this, but that's how we're going to use this. We're going to just look through where are peaks showing up in these molecules and tell us, oh, there's an OH in this one, or there's an alkane in this one. Don't worry about that. So let's say that you have an IR, but you're going to try and use IR to separate out 2 molecules. This is ethanol, and this molecule is dimethyl ether. What kind of bond could you look at to separate if you had ethanol in a flask versus dimethyl ether? The OH bond in particular. What you would not want to look at is a CO bond. Why? They both have CO bonds, right? So if I look for a CO bond, it's not even, oh, it's over here, right? If I look for a CO bond, there is a stretch I can find. It's in a place that we're going to ignore, and I'll tell you about it later on at this point on Monday. But they both have a CO bond, one here, one there, one there. This molecule, though, and I think I hopefully circled it, nope, has an OH. And an OH stretch is unique. Oops, you can circle things. I'll just underline it. An OH stretch has a unique place where it shows up in an IR. And so if you see an OH present, you would know, oh, there's an alcohol here. Now, it doesn't tell you which alcohol. You'd have to have an idea of which alcohol you started with, but I can tell an alcohol from an ether based on that unique peak. You see how we're going to use that? Okay, we do not have class on Friday. What we're going to do on Monday is go through a couple different functional groups. I have just a couple more slides here. And then on Monday, after we go through those functional groups, we're going to talk about NMR. One more warning. Mass spec, IR, pretty easy. I know you're bored, but this is not that hard. I mean, I'm asking you to do some very basic things. NMR deserves your time in advance. I highly recommend looking at chapter 13 sometime between now and Monday. You don't have class on Friday, so that is a perfect time to spend a little bit of time looking through NMR. The more time you spend on it, the less spooky it's going to be. And we will spend much more than just one lecture on NMR because it takes a little bit longer. Have a great rest of your week. I will see you all not on Friday. We do have lab tomorrow. I'll be there for that. For everybody else, we do not have class on Friday. I'll see you back on Monday. Do you have a quiz on Monday?
Yeah.
You do have a quiz on Monday. I won't on IR yet. Everything up to now is fair game, but we didn't get through enough IR, so I'll leave it off.